All right, greetings. Greetings everyone who's interested in my final project here for the statistics class. Let's pop this open. I'm going to keep it in this mode like this. I'm going to be bouncing around a bit, but I did my project on gun violence in Philadelphia. My goal was to build a spatial regression model to outline some of that data and how it relates to other things, other datum I chose. So, like I was just saying, right? My research question is oriented for the goal. I want to build a spatial regression model to identify what influence blood lead level and population and poverty has on the number of instances of gun violence in Philadelphia Census Tracts. And then I'm including here as one of the dependent variables is location, right? So all three of these two independent variables, and then also making it a spatial regression model. So we're thinking about where things take place. So let's look at all my data. Here we goes my dependent variable, the gun violence. I've done other projects on this. I think it's a cool data set to check out. This link right here will take you to it. I already have it pulled up, really. It's if you just Google exactly that, real simple, it takes you to this, the city of Philadelphia's office controller. And it presents this dot map of not just homicides, but anytime there's a reported victim of gun violence. So it'll tell you who was shot. So every time somebody gets shot, fatal or non-fatal, it'll show you. You can explore this on your own. It goes all the way back to 15. Like we can check out 2021 was the pandemic year, right? And that was the high score. I shouldn't say it like that, but that was the highest Philadelphia got. I'm working with all of the data I'm working with is all these years. So all the way from 2015 to 2023. Let's get rid of that. Here's a little map I made in R just to check it out. We got 5 little sections, and you can see the darker stuff is definitely clustered around. You can ignore stuff like this area down here and the big open park sections, because what that data is looking at is comparing these instances compared to the population and things like where the airport is, and then also Fairmount Park is a big area it's easy to pick out. Nobody lives there, so of course these are going to have like high rates, because if anything happens, it's compared to no population. So you can see the cluster in there. Let's check out the other data I'm going to use. I picked out a data set identifying mean blood lead level in Philadelphia. I got this from another class. Here's a CSV, just with the geoids. And we got other stuff. It was identifying, I think the number was above 5% in your bloodstream or something. But I'm just going with a mean blood level. So people have more blood on average in there for the population of a census tract, really. They have more blood. So you can check out that. We only got 3 things, but you can see the clustering seems to be in the same place in that central north area as the gun violence. And same with the poverty count here. It's just a count of how many people of the population from the census tract. This is census data that it's just a hard count, and you can see the clustering's almost in the same spot. So from already just a visual accounting of our data set here, everything seems to be in the same location. So that tells us it is a good idea to be building a spatial regression model. Excuse me. So let's build our linear model to start out. Real simple. These are in the data, that's just what these things are called. But really, it's gun violence and mean blood lead levels, population and poverty. Now, what we're checking out with this is, yeah, it's pretty significant right here. Got it, PowerPoint. We got a multiple R squared of 0.635. All these intercepts are significant. Looks like there's a pretty good correlation between all these data sets. But can we make this better? This is already a pretty good model. Can we make this better? So we're going to explore two different methods of building a spatial regression model. And first one, we look towards the residuals of what amount of the data and what amount of data is like unexplained, right? Unexplained by this linear model. And that's about 40% based off the R square. So let's check it out with some maps. Maps and plots. Our residual map shows the clustering of significant residuals, right? Of the bigger one, it definitely seems like it's clustering just looking at it. And the higher ones are all around each other, and even the right around 0 are all around each other. At least that's what it looks like. And looking at the QQ plot tells us, yeah, it's pretty much right. It follows the line pretty strong until we get to the end. There's a couple, these numbered points are specific pieces of the data set that R studios identified as like outliers, right? So let's do some actual statistical tests of the Moran's eye on those residuals. And we're taking at that we got an observed Moran's eye at this 0.3, and then the expectation was 0.00, negative 0.005. And it tells us right here, alternative hypothesis greater. So that means that the null hypothesis of Moran's eye is that there is no spatial clustering. There is spatial randomness. So we deny this null, accept the alternative, and there is spatial clustering in the residuals. Okay, so that's a direction we can go. I also want to look at a lagged mean map right here. So this is a lagged mean of the dependent variable. So that is the counts of gun violence, each instance of gun violence. You can see it definitely looks very organized, very spatially clustered. But same thing as before, we're running a Moran's eye on that. And we got the same thing, everything's significant. The expected value is very different from the observed. And the alternative hypothesis is accepted that there is spatial clustering in the lagged mean map of the dependent variable. So this is I think just a recap, right? Yep, both of those Moran's eye tests came back significant. Residuals, the linear model are clustered in some statistically significant way, and the dependent variable is spatially correlated by itself. All right, so looks like both of these directions are pretty strong. And right here, this set of Lagrange tests is also telling us that. These first two over here is all I'm really trying to pay attention to. These robust models are less significant. The p-value right here, less significant than over here on these two, the error model and then the lag model. These are both significant. So we're gonna, like the data I just laid out for us, we're gonna check that out. We're gonna go deeper into that because these are both really significant from these Lagrange tests. So the spatial lag model first, let's check it out. This row unit right here, this is pretty much, you can think of it like the lag, or sorry, not the lag, the slope, the general slope of the model. And I did this impact test down here. You can see where these direct, indirect, total. Let me hold my notes for that. Impact. So you can think of that as increase our x by 1, right? So increase that, whatever the that independent variable is. And then the direct rate is how it affects just the one, whatever census tract we're trying to identify, and the indirect value is how all the neighbors of that census tract are affected. Or increase all, yeah. But really what we're checking out, because we want to see if this model is better than, we're seeing if this model is better than our LM model. And right here, the AIC score, which is exactly that. They test to see how well the model fits the data. And the lower the number, the better. Or right here, we have a lower number compared to right here, it tells us even the LM AIC score is higher. So it looks like our spatial lag model is better than our spatial, or than our just linear model. So looking good so far. Let's check out the spatial error model. Right here, this lambda value, that's our slope type value. And then, right, we would ideally just be able to check another AIC score and see if that's lower. But right here, we don't have this for this type of model. So we run a spatial Hausman test over here. Now, what is that? The spatial Hausman test is comparing, it's testing this null hypothesis. It's seeing if there's any difference in coefficient estimates from the OLS model and then this spatial error model. So we are getting a significant value here, meaning we are going to deny the null. We're rejecting the null because there's a significant p-value. The alternative hypothesis says there is a systemic difference in the difference in those coefficient estimates. So that gives us the direction that that model probably isn't that good. So good thing, that's all right, because good thing we have the lag model to work with. And I think that's the one we're going to be doing. Let's go back to our research question. What influence does blood lead level, population poverty, and spatial distribution have on the number of instances of gun violence in Philadelphia Census Tracts? We're building a spatial regression model to represent this influence. And through all the tests we have done, we have determined that, yes, we should be doing a spatial model in the first place. That is good. And then as we tried to build one and we explored these two different types, we decided the spatial error model was not appropriate, and that the AIC score of the spatial lag model was lower than the simple linear model. So we decided that's more appropriate for our data. And that's the finish line right there, that we decided this spatial lag model I built in R is appropriate. Now, I don't have the exact formula for you, but it's all sitting in R, so we're all good. Thanks for listening. That's my final project.